My name is Dhara Patel and my teammate name is Subham Gulia. We are presenting the two-dimensional fair queuing for multi-tenant cloud services. The authors are Jonathan Mack, Peter Bodick, Madan Lal Musuwathi, Rodrigo, and the Krishnanan Vardarajan. I would like to tell you first what we are covering in this presentation. First, I will be presenting the overview, motivation of this paper, and after that the design and main idea of the paper, evaluation of topic, limitation, proposed solution, and conclusion will be presenting by my teammate Subham. Let's begin with the overview. In the cloud services, different tenants execute their request in the thread pool of the same processes, which requiring the fair sharing of the resources. However, using the fair queue scheduler to provide the fairness to all the tenants, it's not a easy job for scheduler. There are some challenges for the fair queue scheduler, such as the resource concurrency, large cost variance, and unknown and unpredictable resource cost. Let me give you some more detail about these challenges. First one is the resource concurrency. Suppose if we have the five threads for execution, then they all should be the execute concurrently. Thread pools in the said resources execute many requests concurrently, often tens or even hundreds or maybe the thousand. But whereas the packet scheduler are only designed for the sequential execution of request. And the you can see here the second one is the large cost variance. The request cost vary by the least order of magnitude across the different tenants and the API types, from maybe sub-million second to many seconds. And the third one is the unknown and unpredictable resource cost. Execution time and the resource requirements of the request are not known at the scheduler time. That are a difficult task to estimate the cost of that particular resource. However, these all challenges must be addressed for the better uh, scheduler. Okay, this the challenges which we just understood that affect the quality of schedules produced by the algorithm, such as the WFQ, which is weighted fair queuing, and the worst case fair weighted fair queuing, which is the WF2Q. Let me describe what is the WFQ and the WF2Q. Here, the WFQ is the data packet scheduling algorithm which is used by network schedulers. WFQ is also known as the packet by packet GPS, since it approximates the generalized processor sharing to within one packet transmission time, regardless of the arrival patterns. And the WF2Q, it's similar to the WFQ algorithm, but the WFQ does not schedule a packet until it is eligible. So that's the difference between the WFQ and the WF2Q. The incoming packets are placed into the regulator where they will wait to become the eligible, and then they are put in the scheduler. I- In the WF2Q, the process are like this. Let's take a look in these two figure. Here you can see that we have the four tenants A, B, C, and D sharing the two threads. Tenants A and B send the request with 1 second, while the C and D with the 10-second duration. Okay, we can see in the figure 1 or figure A, which is the busty schedule. The service rates allocated to tenants A and B oscillates significantly because the C and D have the large request. As we just saw that the C and D has the 10-second request, which is more than A and B tenants request. It is likely that the many or maybe all threads will be blocked for an some period of time, and small request will have no access to resources for some time because the C and D have the large request time. To avoid the producing the bursty schedule, the author identify here the cause of the bursty schedule is in the WF2 queue, which is the worst case fair weighted fair queuing as the eligibility criteria that applies to uniformly across all the threads. In other words, we can say that if the request is ineligible for one thread, then it is ineligible for all other threads as well in the WF2 queue. So the later on 2DFQ, which is the two-dimensional fair queuing, has been introduced, and the 2DFQ is designed to generate the smooth scheduler. It produces the smooth schedules. We can see here in figure 2, even in the presence of the expensive or unpredictable tenants, the 2DFQ improves the per tenant services rates as compared to the WFQ and WF2Q. The 2DFQ spreads the request of a different cost across the different thread and minimize the impact of tenants with unpredictable request. Uh, why there is the need of the fine grained resource isolation? There are many important data center services such as the storage, database, queuing, and the coordination services are shared among the multiple tenants. In the distributed system s- shared by the multiple tenants, effective resource management is one of the important prerequisite to provide the quality of services or maybe the guarantee. However, providing the performance guarantee and the isolation in the multi-tenant distributed system is extremely hard. It's not easy because the tenants not only share the fine-grained resources within a process, but they are also uh, share or across the multiple processes and machines along the execution path of their request. In the most of the systems, the multiple tenants contend with each other for resource within the same set processes. Example include the performing the metadata operation on the HDFC name node and the performing the data operation on the HDFS data node, where the HDFS is the Hadoop distributed file system. When tenants compete inside a process, traditional and well studied resource management techniques in the operating system are unsuitable for the protecting tenants from each other. In such type of cases, the aggressive tenants can overload the process and gain a resource or gain the unfair share of the resources. So, in the extreme, this lack of isolation can lead to the denial of service to well behaved tenants, and even sometimes the system wide may be outage. We can take an example. For example, the eBay Hadoop cluster regularly suffered from the denial of service attacks caused by the heavy users overloading the said HDFS name node. Okay, now the next there are two desirable properties for the fair scheduler. The first one is the work converging, in which the worker thread should always process some request when it becomes the ideal. And the other one is the scheduler should not be busty when it's servicing the different tenants. Let's look at the one important topic, which is the fair queuing background. The WFQ keeps track of the work done by each tenant over time and makes the scheduling decision by considering the work done so far and the cost of each tenant's next request. And what does the WFQ do is it extends the WFQ and is widely considered to have the better fairness bounds. WF2Q restricts the WFQ to only schedule requests after they become the eligible. So we can say that the WF2Q is the more restrictive than the WFQ, because when the request become eligible, then and only then it get proceed. Okay. Let's have a look in this figure. It describes that how does the WFQ and WF2Q works. Here the four tenants sharing two workers threads. Tenants A and B have the request size 1 and the tenants C and D have the request size 4. Here we can see that in figure A, that is the ideal schedule of request over threads in this scenario. Tenants A and tenants B has the small request size, which is running on the thread W1, where tenant C and D has the large size as compared to A and B, and which is running on the W0. So A and B tenants will not be blocked for the long time, because we can see that here in the figure they are running on the different threads. Okay, in the figure B, which outlines the virtual start and the finish time for the WFQ and the WF2Q. So there are given the start time and the finish time of the both algorithms on for the A, B, C, and D tenants. In the figure C, you can see that the resulting schedule for the WFQ. Since the WFQ schedules request in the ascending order of the finish time, it uses both threads to execute the four requests, each for A and B. So only at t is equal to 4 do C and D have the lowest finish time, causing the WFQ to simultaneously execute one request each for C and D, which which occupying the thread pool until the t is equal to 8. So this schedule is busty for A and B because they each get a period of high throughput, which is followed by the period of zero throughput. In general, the WFQ bursts are proportional to the, we can say that it's a proportional to maximum request size and the number of tenants presented in that scheduler. In the figure D, it shows that the result of the schedule under the WF2Q, which also has periods of blocking proportional to maximum request size. The WF2Q also schedules the request in the ascending order of finish time. But with the additional condition, uh, we just discussed that the WF2Q is it does not process the resources until it gets the eligible. As a result, the WF2Q does not schedule the second request of A and B because their virtual start time is 1, which means they cannot be scheduled until t is equal to 2. So only the remaining request for WF2Q to pick, and those are the C and D. So like the WFQ and the WF2Q both are produce the busty schedule services for A and B, followed by the concurrent service for C and D. The bustiness occurs under the WF2Q when the multiple worker threads become available and only the large requests are eligible to be scheduled. Now let's have a look at the 2D FQ. we will see from this figure how does the 2DFQ it works. The 2DFQ, the two-dimensional fair queuing, it modifies the WF2Q's eligibility criteria to make the request to eligible at the different times for different worker threads, which avoiding the WF2Q all or nothing behavior. 2DFQ is the uniformly staggers each request eligibility across threads, making them the eligible to run on the high index thread and the low index threads. With this modified the eligibility criteria, each worker thread has the different threshold for when the request will become the eligible, while one thread might find that only large requests are eligible, and the other threads might still see the eligible small request and select those one. So the practical effect here in 2DFQ is the partition of the request across the thread by the size of the requestees or size of the tenants. Small requests become the eligible on the high index threads first, and then the it tends to be dequeued and serviced on those threads only before they are ever eligible for the low index threads. On the other hand, due to the lack of eligible small requests, the low index threads end up mostly servicing the large requests. So in figure A, the modified eligibility times of request under the 2DFQ, which are now different for W0 and W1 both. And the figure B illustrate that the schedule under the 2DFQ. This time, the second request of A and B will not be eligible on W0 until T is equal to 2. But on W1, they are eligible at T is equal to 1. As a result, the 2DFQ schedules C1 on the W0, but it selects A2 for the W1. So here in the figure B, you can see that the C1 is runs on the W0 and the A2 are runs on the W2. And the same process will be continuing. Therefore, the A and B with continuity alternating the request on the W1. In short, our main goal of the two-dimensional fading queuing or 2DFQ is to produce these smooth schedules for the tenants with small requests by minimizing the bustiness over time and over place. Thank you for listening. Now I am going to pass our part 2 presentation to my teammate Subham.